Homework question 11.6 asks us which of the following compounds can exhibit geometric isomerism. There are two main types of geometric isomers that we can think about: alkenes, which have double bonds, and cyclic systems. So for alkenes, each carbon must have two different groups on it. For instance, if we consider this alkene, this can't have geometric isomerism, and that's because what we're mainly looking for is that the two substituents on the carbon could switch, and we'd see in a different structure. If this hydrogen switches with the other one, we still have the same alkene with a carbon attached to two hydrogens. In order for this to work as a geometric isomer, we need this carbon to have two different groups and this carbon to also have two different groups. So if we were to exchange these two groups on this rightmost carbon, we would then see the hydrogen on top on this side and the methyl on the bottom. These are two geometrically different isomers. Here we have the two hydrogens on the same side of the double bond, and on this one, they're diagonal from each other. In terms of a cyclic system, let's look for instance at cyclohexane. First criteria states that each ring must have two non-hydrogen groups on different carbons. These groups must also be able to change orientation. On this carbon, pointing towards us, on the one next to it, pointing away from us, a methyl group. So these are two non-hydrogen groups on different carbons, so that checks that criteria. They can also change the way they're pointing. So let's say in this one, the bromine stays pointing towards us, but then the methyl group is pointing towards us as well. These are geometric isomers of each other. Taking this into consideration, let's go through each of these compounds and see if they exhibit geometric isomerism. Starting with A, we see that it is a cyclic compound, so we want to use the rules for cyclic systems. The first rule states that each ring must have two non-hydrogen groups on different carbons. We do have two different non-hydrogen groups. We have this ethyl group and this methyl group, but they're on the same carbon, not different carbons. And so A cannot exhibit geometric isomerism. B is also a ring system. It has two non-hydrogen groups. It has this methyl group and this sec-butyl group. They're also on two different carbons, so they follow the rules that we need, and so B does in fact work. Moving on to C, we could first think that we should be following alkene rules here since we do have a double bond, but since one of the substituents is a ring, we can't break this apart and move it around. And so we should consider the cyclic systems as a more relevant set of rules to determine if we can have geometric isomerism here. So the first part of it states that each ring must have two non-hydrogen groups on different carbons. We do have that. This carbon has a methyl group, as does this one. It also states that groups must be able to change orientation. Both of these carbons are sp2 hybridized, which means they are trigonal planar and therefore flat. If they're flat and in the plane of the screen, they can't change their orientation, and therefore C does not work. Looking at molecule D, we see that it is cyclic, so we're going to look at cyclic rules for it. We see that it does have two non-hydrogen groups, so we have this methyl group and this isopropyl group. They're also on different carbons. These aren't locked in by any sort of sp2 hybridization, so they can come towards us, they can go away from us, and therefore molecule D does work. So lastly, we're looking at molecule E. It's not cyclic at all, so we're just going to look at it in terms of alkenes and these double bonds. Each carbon must have two different groups on it. Focusing first on this double bond, we see that this carbon does have two different groups. It has a hydrogen and then this alkyl chain, but this carbon has two methyl groups. If we have two of the same groups on one carbon, changing them around won't change it geometrically, and therefore this double bond does not give us geometric isomerism. If we look at this double bond instead, we see that we have a methyl group here on this carbon and then the rest of this alkyl chain. So this side looks good, but this carbon has two hydrogens. And since we have two of the same group, we again don't see any change when we invert these, so E does not work. So our overall answer to this will be E and D.